Well, a very good afternoon to all speakers, participants. So, as I'm Dr. Debashis Panda, convener of the program, heartily welcome you all to today's international webinars series on novel materials and devices for supercomputing 2020, organized by Department of Physics, National Institute of Science and Technology, Berhampur. As some of you are not joined yesterday, for that, I like to remind you once again to attend the whole series. You all please use the same link, whatever provided to your email. A feedback link will be provided in between the talk in your chat box. Kindly send the feedback as soon as possible. Certificate will be provided after getting the feedback only. All are requested to write your queries to speaker about the talk in chat box only. I request you all, please close or stop your video and mute your audio. So the National Institute of Science and Technology was established in the year 1996 by a group of academicians and technocrats educated in the top-notch institution of India as well as abroad under SML Charitable Educational Trust. This is the first NRI educational venture in the state of Odisha and southern Odisha. Keeping true to its core value and mission and vision, NIST has become a top-notch institute in the state and country since establishment. So now I like to introduce our distinguished speaker, today's speaker, Dr. Tarapada Sarkar. Dr. Sarkar, working on the novel electron-doped superconductor semiconductor with a group of one of the finest experimental physicists, famous in the high-temperature superconductor, Professor L. Green. The goal is to understand the mechanism of superconductivity in the cuprates. This is the one of the major unsolved problems still after 3 decades. And the relation between the superconductivity and the anomalous normal state properties. Prior to joining University of Maryland, USA, Dr. Tarapada did PhD in defects, induced transport properties of titanium oxide thin films under the supervision of pioneer scientist Professor T. Venkatesan, famously known as Professor Venki. I think I'm correct. Professor Venki's lab in Singapore, and who is the director of NUS NNI, National University of Singapore, Singapore. And Professor Aradino at the Department of Physics in the National University of Singapore. He has done his MTech from IIT Kharagpur from the Material Science and Engineering. In this short period of his career, he has received several achievements, which includes received several fellowships to pursue research work, published several publications in reputed high-impact journals such as Nature, that is one of the dream journal for any researcher, Nature Scientific Reports, Physical Review, and many more. Presently, Dr. Sarkar serving as a research scientist at University of Maryland, USA. With this short introduction, I like to request Dr. Sarkar to deliver his talk on high-temperature superconductors from basic to advanced and transferring the screen to Dr. Sarkar. I'm very much sure all of you will enjoy a lot this talk. Please, Dr. Tarapada.
So today I'm going to talk about high temperature superconductors. This talk will be mainly fundamentals. I don't do device stuff, and most of my talk will be measuring resistance, and it's kind of transport, electrical transport and thermal transport. Okay, before I'm going to talk about my work, I just want to acknowledge the people I work with and also the funding agency. Because to do research without friends or collaborators and money, one cannot do really research. You need to have many friends and, of course, the funding agency for the money. And it's really expensive these days doing research, because we actually calculated how much we spend to publish one paper. It came around like 100K per publication, $100,000. per publications. It's huge money. Probably this is one of the reasons India is not doing well in research. Okay, here I work with Professor Richard Green. He's my supervisor, postdoc supervisor. And I also collaborate with Shankar Das Sharma from the center. And there are a few colleagues. Josh, he's a postdoc, Pompa, postdoc, there's another undergrad, Nick. And I also collaborate with Capitonic from Stanford Group, and he's a postdoc, Didi, who is doing some kind of optical measurement, and also graduate student, Zhang. This work is supported by University of Maryland and the Quantum Materials Center, Stanford University, and the funding mostly comes from the National Science Foundation and the Gordon Betty Moore Foundation. Okay, here is my plan. I'll start with the discovery of a superconductor, starting from ONAS discovery to BCS. Then I'll move on to high temperature superconductors, which is known as high TC cuprate. Then I'll talk about a strange metal, bad metals. We'll learn from the transport and the recent discoveries, the ferromagnetic order in these material. What is superconductor? Well, it was discovered in 1911 by Kramer-Ons while he was measuring a resistance of mercury. So what he found, if you see this graph as a function of with temperature, this is the resistance. So what happens around temperature 4.2 Kelvin, resistance becomes suddenly 0. So if you measure conventional metal, assuming there is nothing, the resistance as a function of temperature would look like these dotted lines. So it should follow this line. But instead of doing that, suddenly there is some sort of a discontinuity was observed around 4.2 Kelvin. And this is something different, a phase of this metal, which is known as a superconducting phase or superconductor. So most important property of superconductor is the resistance, which goes to 0 at a certain temperature, what we call as a critical temperature or TC. And not only that, there are a few other important properties of these materials, the superconductors. Is the one is it shows some sort of Meissner effect. It's a very important. Is similar to, I mean, as important as the resistivity is 0. So if you consider this blue sphere is a metal, and if you cool down to the temperature below 4.2 Kelvin, what happens? These metals, basically the superconductors, does not allow any magnetic field pass through this material. And same metal, if you put it in the temperature just above 4.2 Kelvin, the magnetic flux can pass through this material very easily. So what happens below this 4.2 Kelvin, this material becomes a perfect diamagnet. So it repels magnetic flux, passes through it. So there are other properties I won't discuss in details. This it has a flux quantization, and also it shows some kind of Josephson effect. These are the two important properties we actually interested in. This electrical resistivity, which goes to 0. Okay, well, Josephson effect is also a very important one. We use it in many instruments these days. And also the Meissner effect. However, if you apply high enough magnetic field, it is possible to restore the resistive path. So what I mean, if you apply, let's say, H, the magnetic field, which is quite high, higher than critical field, then the resistivity, the resistance will behave like this dotted line. These are the two things were discovered by Kramer-Ons. The first is in 1911, he saw the resistivity as well. Next year, he found that if you apply magnetic field, you can restore the resistive path. Due to this discovery, he got the Nobel Prize in 1913. Now, this is the periodic table. there are many superconductors. The blue ones are the superconductors at ambient pressures. And the greens one are also superconductors if we apply high enough pressure. It took around 50 years to understand why some of these materials are superconductors. And it was a very hard problem. And many people tried to solve this problem, but they failed. And some of them are very, very big and well known in the physics community. So like Max Born, Niels Bohr, Heisenberg, and Richard Feynman, Albert Einstein, all of them tried to solve this problem after the discovery of superconductivity. But somehow they failed to understand why these materials were superconductor. Some of these successful scientists like Casimiro, London, and Ginbal Landau. Finally, in 1957, Bardeen, Cooper, and Seyfert, they gave the microscopic theory to understand the superconductivity in some materials. But I don't want to say that they are not smart enough, all these big scientists. Actually, the main problem in those days was that there was no quantum mechanics. So quantum mechanics was just developing during the discovery of superconductivity. That was a main problem. So there was no microscopic theory to understand, to explain these superconductivity in this material. Now, how do you understand superconductivity? Well, why some of the materials shows no resistance? Now, this is a cartoon picture. I'm just trying to keep everything very simple. So these red balls are atoms. They form a solid because to minimize the electrostatics energy. Now, in all these atoms, there are in the outermost cell, it has electron, which are basically the free electrons. They can move around the crystals and they can carry current. So while they carry currents, they can bump into things. That is some kind of a scattering. This is what actually we call is a resistance. So when these electrons move through the crystals, if it is carrying current, if it is scattered by some things or bumps, things could be many things. It could be some defects. There are many things. Then we lose energy or current that's converted into a resistance. Now in superconductor, what happens? There is no resistance. How do you explain it? Well, from the experiment, it was clear that in superconductors, two electrons comes together. Basically, they form a pair. Once they form a pair, then the scattering is very less, or there is no scattering. That means there is no resistance. Now the problem is, how do we combine two electrons together, or how two electrons pair? Because if you have two similar charge, they cannot come together. They should repel each other because of the Coulomb interaction. Now, the first key experiment, the clue came from the isotope effect. So what is found in this isotope effect experiment is that TC is different for different isotopes. That means somehow the superconductivity is related to the ions. So there is some sort of ion and electron interaction is going on. Then it was later realized that yes, ion could bring two electrons together. Very simple picture is there here. So let's say these atoms are vibrating these red balls. These are positive ions, the center. Now, if electrons pass through these atoms, so this negative charge, that can actually deform the lattice. So two positive ions can come close together, and there will be effective positive charge, and that can attract an electron here. So this is how two electrons can form a pair. So basically, if there is a high enough electron or phonon interaction, one can have a pairing of electron, which gives the superconductivity or loss of resistance. So what happens in theory? It forms a Cooper pair, and two electrons which are fermion. If you add them together, when they form this pair, Cooper pairs, it becomes a bosons. That allows all these Cooper pairs basically can occupy the lowest energy state, same energy state, and can pass through the solid without a loss of any energy. Basically, resistance becomes zero. And in theory, it was found that this it forms a gap. Those I didn't prepare everything here. Is in the Fermi surface, it forms a it opens a gap in the Fermi surface, which is delta, that defined by these equations, and the Tc is directly connected to this energy gap. Now, when there is a phase transition, it breaks some sort of symmetry. In theory, in superconductor, it breaks a gauge symmetry. Those are in theory. I won't discuss any of those things. I'll mainly focus on experiment and a little bit of equations and some understanding of the theory. Now, it was fine, because this BCS theory can explain why some of the materials are superconductors, why two electrons form a pair. Now, when we say we understand superconductivity according to BCS theory, is that now one can theoretically calculate the superconducting temperature of any material, because if you know the crystal structure of the materials, if you take the pen and notebook, you can calculate what would be the Tc for that particular metal. It was fine, BCS theory was working until 1986. But in 1986, these two gentlemen, Benoit and Muller, discovered a new type of material, this lanthanum barium copper oxide. These materials are known as cuprate. And Tc of this material is around 30 Kelvin. Next year, Paul Chu discovered a different material, YBCO, and it shows Tc above liquid nitrogen temperature. Now, this material cannot be explained by BCS theory. So BCS theory failed to explain superconductivity in this material. And these are known as high temperature superconductor or cuprate superconductor. Because of this discovery, in 1987, they got the Nobel Prize. Now, there's one interesting story about this discovery of YBCO by Paul Chu. This paper was actually published in PRL. So when he submitted the paper, what he did, he wrote, instead of Y, he wrote YB, because he was scared that, because if you know that the LBCO is a superconductor, it is very easy to prepare this material, and one know the composition of other materials. Easily someone else can reproduce the data and publish the paper. So that was one of the reasons. Most likely he changed during his submission. Instead of Y, he wrote everything YB. Now, when the paper was accepted, after the proof check, he changed from YB to Y. And he published the paper. It is not a good idea to do this kind of stuff, but somehow he did, because of his, it's very easy to prepare these materials. Now, why high temperature superconductors? There are many reasons. Because if we somehow can get this tungsten temperature above room temperature or near room temperature, we could do many things. It will change the whole world. some of the examples are like maglev train, and this one is one motor. This big one is a ship propulsion motor. We use it in this kind of ship, made of copper wire. This tiny one is made of cuprate wire. In fact, in Scientific American magazine in 2010, they named 12 events that will change the whole world. And one of them was room temperature superconductors. And some of them are like, if there is a conventional war, if there is a nuclear war happens, what will happen after the war? And what will be the situation if all the glacier ice melts down? And they also included this room temperature superconductor could be one of them, because that will also change the whole world. Now, to get the room temperature superconductor, we need to understand the mechanism, because it doesn't obey the Debashis theory. Also, there is no theory which can say anything about where to look for the high temperature superconductor. There's nothing. We do not understand any of these. Now, in terms of material, so there is a big shift. If you see these materials, these niobium, gallium, all these materials, up to this material, these are known as Debashis superconductors. So all this material could be explained, or one can calculate theoretically what will be the TC of this material using Debashis theory. And these materials are known as high temperature superconductor, and these are the first material that shows superconducting TC above boiling temperature of the liquid nitrogen. So one could cool down these material very easily. Just have to take liquid nitrogen to get the superconductivity. Now, in terms of crystal structure, the main difference is that all these superconductors below this one more or less has a cubic crystal structure, but these superconductors has tetragonal crystal structure. This in terms of crystal structure. Now, the other thing is that everything in this material is happening only in this plane, this copper oxygen plane. So the resistivity or superconductor, everything is controlled by this plane. And all these regions work like a charge reservoir. So in terms of theory, if we say we say something like that there is a very weak correlation between these two planes. That means that if you measure the resistivity along the c-axis, will be very high compared to the resistivity in the AB plane. This is the reason we call these materials are quasi 2D. These are complex, so this is also the layer structure. Now, there are other important things. There are many different. The other important thing is that all these material, these Debashis superconductors, are metal. So, but this material is not metal. This is a insulator. So superconductivity was found in a material which is insulated by doping. Now, how do you understand a normal metal? How electron moves in a normal metal? Let's assume this is a crystal structure. These are the atoms, and these black dots are electrons in the outermost cell. Now, whenever there is a empty space, because electron, this double occupancy is discouraged by the Coulomb repulsor because of two electrons of the same charge, they will repel each other, they won't allow take the same same cells, same position. Now, if you have an open space, this electron can move to the next atom and hope one another. This is how this electron can flow in simple matter. This is a very simple picture. Now, what happens in these cuprate superconductors is very different. In copper, all the sites are occupied. So there is no empty space. So electron basically cannot move from one side to another side. And these materials, this is why these materials are insulator, and these are known as correlated insulators. However, one can dope this material and get it metallic or superconducting. So how do you do it? If you dope this material with a different valence element, like lanthanum has 3+. Now, if you have a strontium which has a valence is 2, then there is a one electron missing. That will create an empty space. Then this electron can move from one side to another side. This is a whole dope example. Same thing can be possible if you dope with electron, can have extra electron, and electron can move to the slide. However, this electron side is a bit complex here because this is a bit of, which is not understood yet. But this is a very simple picture. Now, there are many superconductors, but these superconductors are divided in two groups. One is whole dope, this YBCO, BISCO, or LSCO, these are whole dope superconductors, and TC of these materials are quite high. The other systems where I am working on is electron dope superconductors. These materials are doped with cerium. And most of my talk will be on this material, is lanthanum cerium copper oxide. And the number of reasons we work on electron dope superconductor is that TC of this material is low. If the TC of these materials is quite low, then it needs a very low magnetic field to kill the superconductivity and restore the resistive state. And in our study, mostly we are trying to understand the mechanism of this normal state. Normal state means when there is no superconductivity, means if we apply high magnetic field and kill the superconductivity, restore the resistive state, and study that metal. This is the phase diagram of this LCCO material. This is temperatures versus doping. If there is no cerium, that means this is the parent compound, is an insulator. And also it is an antiferromagnet. So what happens in copper, these pins are aligned antiferrolal, which gives antiferromagnetism. With doping, if you increase the doping, means cerium concentration in this material, what happens? This nil temperature, this blue regime, decreases and it vanishes around doping 0.07, then the superconductivity emerges. There is another regime, this light blue regime, we call it short range antiferromagnetic regime or fluctuations. Basically, you can say some sort of weak antiferromagnet. And this dome is the superconducting dome. So what happens with increasing doping, superconducting transition temperature peaks around 11% doping, then it comes down and goes away around 17.5% doping of cerium. then it becomes a normal metal. We call it Fermi liquid, which I'll discuss later. And recently I found not only it's a normal metal, it's also a itinerant ferromagnet. Now, before going to discuss about the measurement and result, I just want to tell you how I prepare these samples. In Maryland, we use PLD, pulse laser deposition, to prepare this thin film of this material. So you can see this is a target, we call it target, basically a coin-like thing made out of this material, lanthanum cerium dope, lanthanum copper oxide. And PLD is nothing but just a steel chamber and attached to some pumps. And inside this chamber, there is a heater. You see the red color heater. There's a target holder, means the material which I'm going to deposit on top of the sample. Sample is this one, this square, very small square one. That's the sample, which is sitting on top of the heater. And we use pulse laser, which is hitting this target, evaporating the materials, and at high temperature, they're sitting on these samples. That's how we prepare the thin films of this material. Once we prepare these thin films, we do some basic characterization. The first thing to check is that is the film is quite uniform, or is kind of some patches of film. To make sure we see the surface of this film, they are very clean and clear. And also we do X-ray to check the crystallinity of the sample, also whether it's growing epitaxially or not. We do sometimes AFM to measure the roughness of the film. And we have to know the thickness of this film as well. For that, we do SEM, scanning electron microscope. So this is the film you can see sitting on this strontium titanate substrate. The thickness of these films are in the range of 100 nanometer to 200 nanometer, depending on our measurement requirement. We prepare them, whether it's 100 nanometer or 200 nanometer. So once we are sure that this material, this film is quite well, it is epitaxial and quite clean, then we check the material composition. Material compositions are verified using WDS. Material composition is verified by WDS, and also there are other way one can check that these films are doping concentrations are consistent or not. For that, we measure the C-axis lattice constant. So as a function of cerium doping, you can see that's how the C-axis lattice constant is changing. So combination of all these methods, we verify whether these stoichiometry of all these films are intact or not. Once we are done with that, then we start to do the transport measurement. Now, why transport? This electrical transport is fundamentally very important, and it is very powerful because it contains many important information. It gives details about the microscopic physics. Because we study the charge and energy, those are the conserved quantity. And in fact, most of the Nobel Prizes in condensed matter physics have been for the measuring resistance. So measuring resistance is a very powerful thing. I mean, this resistance gives many information about the microscopic physics. Here is a cartoon of normal metal. So if you take, let's say, aluminium or any other metal and measure the resistivity or resistance versus temperature, how it looks. This looks like quite similar to this one. So what happens at low temperature, we call these are, if it follows Fermi liquid theory, and if electron-electron interaction dominate, then what happens at low temperature in this bend regime, one can fit with these equations. So basically, if at low temperature it fits this equation, then one can say it follows a Fermi liquid theory. And also one can measure the magnetoresistance of this material. Also, magnetoresistance is quite similar to this one. So if you just take out, I mean, basically magnetoresistance will be also very similar to this one. You will not have we won't see this linear in resistivity or linear in age, but other than that, it will be quite similar to resistivity as a function of temperature. We also measure thermopower. Thermopower for normal metal, if it follows this formula theory, this thermopower is also proportional to temperature. So what it means, if I divide by temperature, S by T is constant. I'll explain what is thermopower later. I have few slides, I'll explain those things later. Now, if it is a conventional metal, we know there are well-established theory which can explain all this material and the scattering mechanism as a function of temperature. Now, what happens to this material, these high temperature superconductors? What we found, if you take this LCCO or any electron doped superconductors, resistivity as a function of temperature in all these regime, it is T square. What one would expect in this regime, you see, resistivity as a function of temperature because of this electron photon scattering should be linear. Instead of linear, it is T square. So this behavior is quite strange. And not only that, this blue one is a superconductor. It has TC around 15 Kelvin. Now, if we apply magnetic field around 8 Tesla, we can restore the resistive state. So this is the resistive state. What happens? This resistivity here as a function of temperature shows linear behavior. As we have seen in normal metal, we should see kind of like this. So there would be some kind of saturation and also bend. It should follow this kind of T square behavior. Instead of doing that, it shows linear behavior. And that linearity was measured down to 20 millikelvin. This work was published from this Maryland group, from our group in Nature. And so what it tells that these materials are not quite similar to conventional metal. And probably this resistivity as a function of temperature is linear down to 0 temperature. This is very strange. And this is the reason these materials are known as strange metal. Do we understand why these materials are strange metal? No. There are many explanations, but still not. But there is still no clear understanding of this strange behavior. There's a recent one which is accepted in Nature Physics. Actually, these data are my data, and I sent it to some of our collaborators, and they published the paper in Nature Physics in 2019. They claim that this strange behavior, something is Planckian. There is no theory, it's just a conjecture. What it tells that the scattering rate, this tau, is basically resistivity, is equal to thermal energy. If you just take out this h curve, multiply that, h curve by tau is equal to thermal energy. So if you put a constant in front of this kBt alpha, the alpha should be 1. If it is Planckian, this alpha should be 1. So what they found, they took the ratio, this resistivity, here it is written as in tau, but this from the this Drude model, one can, everybody knows this, what is resistivity and the tau relation is sigma equals any mu, one can calculate that. So from that calculation, they found this alpha equals to 1.2. That means very close to 1. That means it's a Planckian. Now there is a problem with this explanation. The problem is this. Now this red line is basically the line is here, this green line. Now if we extend this red line, what happens? It should follow this one. But what happens in this material, resistivity in the intermediate temperature regime, it crosses the Planckian limit. So when I say a Planckian limit means, if we consider the resistivity, if it is 1, it cannot be higher than this line. So how do you then explain this resistivity? So it actually violates this Planckian idea. At least this is not Planckian. And also the concept of Planckians is very complex, and it's a conjecture. There is no theory. It's not theoretically calculated using any quantum mechanical model. It has also other strange behavior. Beside this linear in T resistivity down to 0 temperature, we measure the magnetoresistance of this material. Up to 65 Tesla, we found this magnetoresistance is also linear. So basically this line goes all the way to 65 Tesla, which is linear, but that should not be the case. In the low field means omega c tau is very, very less than 1. This should be quadratic. So it should show some kind of h square behavior. But it doesn't do that. It shows linear behavior all the way up to 65 Tesla. We also measure the thermopar. What is thermopar? Thermopar is very similar to measuring resistance. When you measure resistance, you basically create electric field gradient, or electric field gradient is created in the material. We measure the potential difference between two ends divided by the current, then we can get the resistance of the material. Now thermopar is very similar. Instead of electric field gradient, we just create a temperature gradient or a thermal gradient. So this is the hot end and this is the cold end. When there is a temperature gradient, it develops a voltage. And that this delta V divided by the delta T between these 2 points, the temperature gradient and the potential difference, is the thermopar. Now, as we have seen that S by T, this thermopar, this S is proportional to T. So S by T basically should be constant in conventional metal. But what happens in this strange metal, this S by T is not constant. It is some sort of logarithmic. It doesn't show conventional metal-like behavior. This is also again strange. This S by T logarithmic behavior is seen down to 2.3 Kelvin, for 40 Kelvin to 2000. So I just want to remind you that all these properties we are talking about at low temperature. Low temperature means below 40 Kelvin or below 20 Kelvin. So below 20 Kelvin or below 30 Kelvin or 40 Kelvin, this should be the behavior of conventional metal. This one was published in PNAS. So now if we go back to this phase diagram of this material, this LCCO, we saw this is the antiferromagnetism, there is a superconducting dome. Now for doping, starting from 15% to end of the dome, 17.5. So 15, 16 and 17, these 3 dopings, if we apply high magnetic field and kill the superconductivity, restore the resistive path, we can get the resistivity as a function of temperature. What we found, we have measured down to 20 millikelvin, and we can feed this resistivity as a function of temperature data using this equation, like a linear equation. Then one can calculate the value of A. So these are the fitting. We can calculate the value of A. Same thing could be done for the magnetoresistance. We can fit all this data using similar linear equation, and one can calculate the value of C. And also for the thermopower, if we fit this S by T with this logarithmic 1 by T behavior, we can calculate the value of ATP. What we found, if you take all these values, this A we got from the resistivity as a function of temperature, and the C from the magnetoresistance, this constant value, and also the ATP, what happens? These values are decreasing with doping, and these black circles, these are the TC divided by the optimal TC. What it means that, let's say TC of this optimal means where the TC is maximum. For 11% doping is 26 Kelvin. Now say 15% doping is 15 Kelvin. That means the 15 Kelvin is divided by 26 Kelvin. That's what the value is, this black one. So what we found, if you normalize this TC, is decreasing with doping. It vanishes around 17.5% doping. It scales with all these constant value. What it means that since TC is decreasing, this A value is decreasing, or C or ATP value is decreasing. Now, whatever be the origin of this linear in T resistivity or linear magnetoresistance or logarithmic behavior of this thermopower is connected to this TC, superconducting temperature of this material. Now, there are some theoretical explanation that this linear in T resistivity or this linear T resistivity could be due to spin fluctuations, which is related to some sort of quantum critical behavior. So what it tells that superconductivity probably linked to spin fluctuation. That was one of the finding in these materials. Now what we learn from all this data, there is a linear in T resistivity, linear in H magnetoresistance, and also anomalous thermopower. Anomalous because it should be constant. Instead of that, it is not constant. It has some kind of logarithmic behavior. And magnitude of all these correlates with the superconductivity. Now this will be the last part of my talk. I'll talk about the recently I found this ferromagnetism. Now this ferromagnetism in this regime beyond the superconducting dome, this is fundamentally very important because so far there is no explanation or some kind of, there is some speculation like the one I just said, probably spin fluctuation is the origin of why TC is decreased, or what is the could explain why TC is decreasing beyond the optimal doping. So since spin fluctuation is decreasing, that's the reason TC is also decreasing. Now why it ends some at some doping like 17.5% doping? This could be explained if we ask if there is a ferromagnetism at the end of the dome. The reason it could explain because ferromagnetism and superconductivity cannot coexist together. So what happens if they compete each other? Whoever wins will exist and other will die. That means superconductivity is decreasing because ferromagnetism is winning. And similar explanation is valid for the underdoped side. So TC is decreasing in the underdoped side because this anti-ferromagnetism is winning. That is the reason why TC is decreasing. So this ferromagnetism is the reason why TC is decreasing. This is the reason why this paper was published in Science. Now I'll go through why we think there is a ferromagnetism. So when I did the magnetoresistance measurement, as we have seen for all these three samples, 15, 16, and 17% sample, this is the 17% sample. What we found, the magnetoresistance is positive. So if we increase the magnetic field, resistance is increasing. Now what happens when you cross this dome? The magnetoresistance becomes negative. So there is a dramatic shift. There's a big change. We measure this low field regime. I did this quick scan. We found that there is a negative magnetoresistance. Now if we do a very low field scan, what we found in 19% sample that not only negative magnetoresistance, there is some sort of loop. This kind of loops are quite a good signature for ferromagnetism. these kind of things are seen in ferromagnetic materials. And this loop vanishes around 4 Kelvin. Now, we wanted to further confirm whether this is a ferromagnetism or not. Then we also found that this loop also direction dependent. Now, if you apply the magnetic field, okay, by the way, what we are talking, all these samples, this ferromagnetism we are studying now, there is no superconductivity. We are beyond the dome. So at low temperature, we are studying. Now, what we found, these loops are also anisotropic, means when you apply the magnetic field perpendicular to the current direction, it has this sort of loop. But if you switch the magnetic field direction, you apply it parallel to the current direction, then it shows this kind of loop. Then we did magnetization measurement. Doing magnetization measurement on thin film is quite challenging, but we did it. After subtraction of the background, we found that there is a loop. This also suggests that there is a magnetization. So these films are magnetic. Now, from all this data, if we compare with the classic ferromagnet, it's well-known ferromagnet, this material, we found these loops are quite similar to this. So this could be ferromagnet. Now we wanted to confirm it further because there is always a mistake. Because ferromagnetism is quite difficult to prove sometimes. Then we went to do other very powerful measurement, is a K rotation. This measurement was done in Stanford in collaboration with the Capitonic. Again, this measurement also shows there is a ferromagnetism. What it means, so in K rotation, this is a angle, this K angle we say, basically it measures the magnetization. It's very similar to magnetic susceptibility. Now, if there is no magnetization, what would happen? This delta theta K should be 0. Now, we see some kind of finite value, and also it changes sign with changing direction of the field. And this also vanishes around 4 Kelvin. Is the temperature where I saw this magnetization loop is vanishing, and also the magnetization is vanishing. So all this suggests that there is a definitely ferromagnetism, and it vanishes around 4 Kelvin. And a magnitude of the magnetization measured using this technique also agrees with the value we found using our squid measurement. So what we found, LCCO is a ferromagnet beyond the superconducting dome, and it magnetic spins are in the plane, and the magnetization we found around 0.06 to 0.08 Bohr magnetron per formula unit. Then we further wanted to confirm that there is no magnetism in the dome. Then we did that we grew one sample very close to the end of the dome. There is a TC, the TC is below 1 Kelvin. So it gives us the temperature. We can check if there is any kind of magnetization or magnetic loop. We did not find any magnet. That suggests that there is no magnetization. So what we found in this material, in the dome there is no ferromagnetic order, but out of the dome, so if you drop this material beyond the superconductor, there is a ferromagnetism. Now there's another, so we went through all these extrinsic origin possibility. We found that this magnetization cannot be from any other extrinsic effect. I don't want to discuss any of these because these are just simple. Now let's say if there is a ferromagnetism. Well, actually this was predicted in 2007 by Sudip Chakraborty. It's long around 12 years ago. He predicted that beyond the superconducting dome there could be ferromagnetism, and there is a quantum critical point. I won't discuss this quantum critical point. What is quantum critical point? Based on the experimental evidence, the experimental data that suggested this could be the possibility is this data. In thallium-2201, this is a hold of superconductors. In this data, this magnetic susceptibility as a function of temperature shows some strange behavior. as a function of temperature, if it is a paramagnet, it should be just inversely proportional to temperature. But instead of that, it shows this odd power law behavior. Now, this power law behavior, 5 by 4, could be possible if there is a ferromagnetic critical fluctuations. Based on these data, he predicted that there is probably at low temperature, there is a ferromagnetism. There are other findings as well. In hold of superconductor in 2010, this LSU also shows there is a possible ferromagnetism, but there's a question mark here because the study they did a mu-SR measurement. Mu-SR doesn't distinguish between antiferromagnetism and ferromagnetism. And based on the theoretical prediction, they thought most likely there is a ferromagnetism beyond the superconducting dome. Now, there's a recent other studies also. This is another material, Bismuth 2201. They also claim, this paper was published in PRL, they found that most likely there is a ferromagnetic fluctuation at the end of the dome. So what we learn, all this data suggests that this ferromagnetism is probably the universal feature of all these superconductors. This high temperature superconductor means there is probably another ferromagnetic dome beyond the superconducting dome. Now, other important thing is this one. Before our observation of ferromagnetism in 2012 from our group, we saw a strange behavior around 17.5% doping. We didn't know. So what was the strange behavior? This resistivity as a function of temperature, it shows power law behavior like 1.6. So we have seen in this regime, there's a power law is linear, but in this regime, this Fermi liquid regime, it's T square at low temperature. But at the crossing point, we found is 1.6. But there was no explanation for this behavior. And also it shows some kind of scaling behavior. From that scaling behavior, it was confirmed that there is some sort of criticality is going on at the end of the superconducting dome. Now, if we assume there is a ferromagnetism, and this power law then could be, because it's very close to 5 by 4 or 4 by 3, is due to ferromagnetic quantum fluctuations. So all this data suggests that this could be the reason why this quantum ferromagnetic quantum fluctuations, because these are some theoretical paper that predicted if there is a ferromagnetic quantum fluctuation, this power law, the resistivity as a function of temperature should be 1.6. And that is what we see, because that's 1.6 means 5 by 3. 5 by 3 is the behavior from the theoretical calculation, and the experimental observation was 1.6. It's very close to 5 by 3. So all this suggests that there is a ferromagnetism and quantum critical point at the end of the dome. So here is my summary. So what we found beyond the superconducting dome, which was predicted 12 years ago by Sudip Chakraborty, there could be ferromagnetism. And we found there's a ferromagnetism as well as there's a quantum critical point. Now, if this is right, then one can speculate the origin of demise of the superconductivity beyond the optimal doping. That means why TC is decreasing when we go beyond the dome could be because of the ferromagnetism. Thank you.
Thank you, Dr. Sarkar. There are a couple of questions are there. First question by Shrikant Mudali. Why there is no theory explaining high temperature superconductor? What are the challenges?
Well, it's a very nice question actually. Now, in conventional superconductors, as I said, these two electrons comes together because of the electron-phonon interaction. Now, the strength of this electron-phonon interaction we need for this high temperature superconductor is very high. And in this high temperature superconductor is not that strong, which can explain the superconductivity in this material. And also it has to be, there are many other reasons, but this is one of the reasons that it cannot, this electron photon interaction cannot explain the superconductivity in this material.
Well, there is another question from same person. What is the highest temperature superconductor recorded so far?
Well, to answer, in ambient pressure, it's around 138 Kelvin. And now, if you apply very high pressure, this halide one, it goes like 250 Kelvin, 250 Kelvin around. At very extremely high pressure is some gigapascal.
I have one question. Just not question, it's a doubt. I saw some data that is in 0 Kelvin. Is it actually possible in 0 Kelvin? I saw some data you show there in some slides.
0 Kelvin. Let me show you then.
Resistivity at 0 Kelvin.
I don't think I have one at 0 Kelvin. I doubt. Let me show. The lowest temperature we went is this one. Okay, it's in. Okay, it is in linear scale. That's why it shows 0, but it was measured down to 20 millikelvin.
20 millikelvin. Okay.
It's down to 20 millikelvin.
So what is the vacuum range in this case?
What is it?
Vacuum means vacuum.
We use a dilution refrigerator where we can go down to 20 millikelvin. It's ultra high vacuum.
Okay.
Minus something, yeah. Not ultra high, probably don't need that. -6 would be fine.
Yeah, I also same question. Whatever Srikant Mudali asked you once again, is it possible to obtain supercomputing at room temperature? Superconductor at room temperature? Is it possible to obtain superconductor?
Well, there is no theory there is no theory that tells that it is not possible. It may be possible. I don't know the answer. That's the honest answer. But maybe possible. I don't know.
But not data available, I think, right?
Yeah. There's no data till now. Well, there are some data, but those are highly controversial. I see. There are questions. Let me answer some. What happened to pseudo gap in high temperature?
Okay.
Well, okay. I didn't see all these questions. Okay, sorry.
So they send you.
Okay, so some of you probably are familiar with this high temperature superconductor. Let me answer this question. The pseudo gap is still not resolved yet. We do not understand this pseudo gap physics. So what is asking, above superconducting TC, there is also a gap. And that gap vanishes at some doping. We do not understand that pseudo gap thing.
So with this, I like to thank once again Dr. Sarkar for making his busy time. It's early morning in USA. See, he wake up at early morning and spend time for us. I'm really thankful on behalf of NIST. I'm also very much thankful to Dr. Sarkar. So I also thankful to all the participants for spending their time. So just I like to tell you once again, tomorrow we have another talk by Dr. Shantanu Jana from Lisbon, Portugal. So at same time. So just this is a gentle reminder. So by this, by thanking once again to Dr. Sarkar and all the participants, all my colleagues. So I'm just concluding today's talk webinar.
Okay.
Thank you all.
Thank you.
Thanks.